12.4, geometric probability. So we can also do probability not just with spinners or dice or coins, but with geometry, more length and area, that sort of thing. So we are going to start off with length. The probability that involves a geometric measure such as length or area is called geometric probability. So if a line segment contains another line segment and a point on the first line segment is chosen randomly, the probability that that point is on the other line segment can be considered a ratio, the length over the length. So if we're trying to choose another point, if we take this line that we started with, line AD, and we want to pick a place to put point E, then the probability of E showing up on this little chunk of the line is going to be the length of this little piece over the length of the whole thing. So if we take a look at the first example, we're going to randomly choose point X, and point X is on JM. JM is this entire line from here all the way to here. And these dots didn't show up very nice. Okay. So we want the probability that X is going to land on KL. So what that means is the probability that X is on KL is going to be the length of KL over the length of the entire line, which is JM. So KL looks like it's from here to here, so that's 7, over JM is the entire thing, so 3 plus 7 plus 4, that's 14. So the probability would be 1/2, or if you want it as a decimal, 0.5, or if you want it as a percent, 50%. Any of those, it's not specifying how to write your probability, so any of those is fine. The next, we want the probability that X is on LM. So that is going to be LM over the length of the entire thing, JM. LM is 4. JM, we already said, is 14. If we simplify that by 2, that's 2 over 7. That's about 0.29 or 29%. And the probability that X is on KM. KM is from here to here, so 7 plus 4 is 11. So we have KM over JM. That's 11 over 14. And that as a decimal is about 0.79, which is about 79%. So a Chicago Transit Authority train arrives or departs a station on the red line every 15 minutes. So assuming you arrive on the red line at a random time, what's the probability that you'll have to wait 3 or more minutes for a train? All right, so let's put in a line here. Okay, so waiting 0 minutes, waiting 15 minutes, right? And we could really say that we're rating 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Wow, I did pretty good spacing. 14 and then 15. Okay. So we want to know what is the probability of waiting 3 minutes or more. So the probability of waiting 3 or more minutes. 3 or more minutes. Okay. So if we say that this entire line is 15, this 3 or more looks like this should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 spaces long. So 12 over 15 would be 4/5, which is 0.8 or 80%. Okay. All right, so area. If a region A contains a region B and a point is in region A, chosen at random, then we want to know the probability of it being in B. So again, it's the same concept. The area of the one you want to know if it's in divided by the area of the entire thing. So when determining geometric probabilities with targets, we assume that the object will land within the target area. So we're not worried about it like missing the target completely, right? If you're playing darts, I know technically you could hit the wall and not the actual target. We're assuming you're going to actually hit the target and not damage the wall, like when we're doing this probability. All right, so I don't know how well this showed up. I'm seeing on my screen it's a little bit difficult to see, but it says to look at the shaded area. So in this, there's some squares that are shaded in. There's just these guys on the diagonal here that are shaded. And then over on the circle, this left half of the smaller circle, and then the right half of the bigger circle. Okay. All right, so we want the area that something is chosen within that shaded region. We need the area of the entire thing and then the area of the shaded region. So the area of the entire thing, if I think of these as almost like units, this is 4 units on one side by 4 units on the other. That gives me 4 times 4. That's 16 square units for the big part. On top, this is 1 square unit, a second square unit, 3 square units, 4, 5, 6 square units. And then 6 over 16, both are even, so that's 3/8. Or if you want that as a decimal, 0.375, or that would be 37.5%. So any of those answers are perfectly acceptable. This is a little bit more tricky. The entire area, the entire area here, we're going to need to use the area of a circle formula. So remember, area of a circle is pi r squared. So if I take a look at this entire circle, it looks like the diameter is 10. That means the radius is 5. So the entire circle area is going to be pi times 5 squared, or 25 pi. And let's leave the pi in there for now to keep it a little more exact. Okay. For the shaded, there's really 2 parts going on here. But I could actually make my life easier. Take a look. We're talking about a circle, right? What if I just took this part and flip-flopped it with this part, right? What if I just traded these guys? Wouldn't that just be half of the big circle? So the shaded is really just half of that 25 pi. So that's 12.5 pi. I could go through the trouble of, okay, pi r squared, r was 2, and then cut it in half, and then add it to this part over here, but it just seems silly. Okay, so we have our shaded, we have our entire, and we need to do the division. So that's 12.5 pi divided by 25 pi. The pi's can cancel out. That is 1/2 over, or that's 0.5, or that's 50%. Okay. You can also use an angle measure to find geometric probability. So the ratio of the area of a sector, right, that's this pink part here, to the area of the entire circle. And don't forget the central angle of the entire thing is 360, okay? Don't forget an entire circle is 360. So we want to use this spinner over here on the side to find these probabilities. So the probability that the pointer is going to land on yellow, and that 45 is referring to this angle in here. So the probability of landing on yellow. So we can do the area of the sector with the area of the circle, but it's the same, it says, as the ratio of the central angle to 360, so that's so much easier. So we're going to say yellow is 45 degrees over the entire circle, which is 360. So that is going to be, let's see, 45 over 360 is going to simplify to 1/8, which is 0.125 or 12.5%. Okay. Landing on purple. Purple is 105. So we have 105 over 360. That simplifies to 7 over 24. So this will be a little messy. That's about 0.292, which is 29.2%. Again, remember, we can write probability any of these ways, so it's not a big deal which one you want to use. This is a little more challenging. The probability of not landing on green. that would be landing on literally anything but green. So it would be the 45 and the 105 and the 70 and the 50. I'm going to land on any of these guys. I could add 45 plus 105 plus 70 plus 50. That would be fine to give me my top number. Or I could just subtract 90. Either way, you're going to get the same numerator here. So I'm going to go with 360 minus 90 because I think that's a little quicker. So when I subtract, that'll give me 270 over 360. But if I added these guys together, that would also give me 270. So it doesn't matter which way you want to do it. Let's see. If I do 270 over 360, that's going to be 3/4, which is 0.75, which is 75%. And then lastly, P, landing on neither red nor blue. So I don't want to land on red. I don't want to land on blue. So that means really I'm going to subtract off the red and the blue. Okay, so I have 360, whoops, that doesn't look like a 6 at all. 360 minus the 70 and minus the 50 to get rid of them. I want the purple